So hello everybody, I'm glad to be here. My trip here was full of adventures, and I'm really glad that I made it on Wednesday morning. It's actually 12 hours driving from Louisiana and 2 days when you fly. So we're gonna switch gears and talk about the world of atomic nuclei. I usually start with a broad picture that shows the phases of nuclear physics, and you can see it's a broad field, starting with quark-gluon plasma that's in the early universe, down to hadron gas, and finally to condensed nuclear matter, which is the focus of our group and the research we do on the blue waters. So as everybody here in this room undoubtedly know, atomic nuclei is made of protons and neutrons, which themselves are which are made of quarks, which are strongly interacting, and this means that the nuclear interactions actually between protons and neutrons are extremely complex because it is a residual strong force. So, for instance, the nuclear interactions are vanishing in a long range. They are attractive at a long range below 2 Fermis to half Fermis, and they are strongly repulsive when the two nucleons get close to each other. On top of that, you have a central force, and there are also other important components which are non-central. So you have tensor and vector forces, and because protons and neutrons are not point-like particles and have their inner structure made of quarks, we also observe that nuclear interaction have not only 2-body forces components, but there are 3-body and 4-body forces, and that makes the whole theoretical study of atomic nuclei quite challenging. There is a great potential discovery in nuclear physics. So the long-standing goal of the field is to be able to derive internuclear interactions starting from low-energy QCD principles, and then use it to model atomic nuclei that are lying at the edge of the existence, which means that they have a large number of protons and neutrons, are therefore unstable. So it's extremely challenging to study them in a lab. And so our hope is to be able to study them on supercomputers such as blue waters. Also, atomic nuclei can be also seen as some sort of labs where you can look and research fundamental laws of nature. And finally, despite the fact that nuclear forces are so complex, we observe rather simple features of nuclei. So, for instance, we see the nuclei tend to deform, they like to rotate, we see clustering. And the question is, how do these simple features emerge from incredibly complicated forces? And so here I'm going to just flash some field of physics where the nuclear structure information is very important. So, of course, it's the whole field of astrophysics, which deals with thermonuclear processes at stars, and when you have an X-ray burst and supernova and all these observing phenomena. Of course, then nuclear reactions are also very important for applied energy studies, and the challenge is to actually calculate the cross-section starting with from first principle, from underlying QCD interactions. And then another field is neutrino and cosmology research, where you have these advanced experiments which, to some extent, rely on accurate information coming from nuclear structure physics. And so what we try to do is to perform ab initio studies of nuclear structure and reaction. And so here you can see just the typical workflow of ab initio approaches. So on the right side, you start with a strong interaction between 2 bodies or 3 bodies, right? So you take the best realistic nuclear potential that people who do nuclear potential give you, and then you use your favorite many-body technique to solve Schrödinger equation and calculate the wave function. From the wave function, you can calculate, you have complete information about protons and neutrons, and you can calculate nuclear properties. And in the next step, you can combine realistic potential with nuclear wave function to perform studies of nuclear reactions. So you can calculate cross-section and reaction rates even for processes which are rare and impossible to study in experiment. The approach that we are using is based on no-core model. This is currently the most popular and universal ab initio approach for nuclear structure. The goal is to solve non-relativistic Schrödinger equation for 8 interacting nucleons, and it proceeds in 3 steps. It's also known as a configuration interaction approach. So you basically choose physically relevant model space because your Hilbert space is infinite, so you have to cut it somehow, somewhere. And you cut it in such a way that the low energy physics of nuclei is within that model space. The standard no-core model is using basis of Slater determinant, which is constructed from single particle harmonic oscillator wave functions. And in the next step, you use this basis of Slater determinant to calculate matrix Hamiltonian, matrix elements. And in the last step, you use Lanzau's algorithm to calculate the lowest like eigenvalues, which corresponds to excitation energies and binding energies, and the wave function. The resulting wave function that you get is microscopic, which means that it obeys polar exclusion principle, and also atomic nuclei is a self-bound system. So it's really important that you are able to decouple intrinsic degrees of freedom from center of mass motion, because you want to describe nuclei that sits in a lab. Nuclei in lab is not like moving around in space. It has center of mass fixed. And it's extremely important for nuclear reaction that you deal with the center of mass problem correctly. And here is why it's challenging to perform no-core model calculation. So on the upper graph, you can see the dimension of the model space as a function of Nmax, which Nmax is some truncation parameter for our many-body basis. And I plot, and you can see that this dimension grows combinatorially with increasing Nmax, but also situation gets more dramatic when you add more nuclei into the system. The red line shows the best calculation you can do on machines such as Blue Waters. So we can actually handle matrix of size 10 billions by 10 billions, which is pretty impressive. However, it's not enough, because what we are getting is converged states only for ground states and some basic properties. But for instance, a Hoyle state in carbon-12 requires us to go beyond current limits, going to Nmax is equal to 20, which means that you have to be able to handle bases that it's of size of 10 to 16. But this is problem. We think the problem is in the basis that the standard no-core model is using, which is the basis of Slater determinants. And so on the picture below, you can see the current applicability of ab initio methods. It's limited only to very light nuclei, and the problem is it's memory bound. So our approach is called symmetry-adapted, no-core model. Symmetry-adapted because we are using a different basis than Slater determinants. We recognize that a nuclei is a many-body system that has many collective features. It likes to be deformed, it likes to rotate. So why don't you use, instead of Slater determinants, why don't you use basis which is tuned to many-body physics of nuclei? And so we are using many-body nucleon basis, which is natural for description of the dynamics. And I use a blue color to depict our collective quantum numbers of our basis states. So you can see, for instance, that each of our basis states carry information about deformation. These are these 2 quantum numbers, lambda mu. For instance, 0, 0 corresponds to nuclei that has a spherical shape. Lambda 0 is a nuclei, would be a nuclear state that looks like a cigar. And then you have 0 mu, which looks like a football. And lambda mu, non-vanishing, corresponds to various triaxial deformations. Also in our basis, we have a capital L, which is orbital angular momentum, which means that our basis is really tuned to describe rotating, deformed many nucleon systems. So three pillars of symmetry-adapted approach are the group theory, because what you see that SU3 and SO3 actually shows the relevant group symmetries. So our basis is actually constructed using machinery of computational group theory. And then we take the best what we can get from nuclear physics, which are interactions, and couple it with high-performance computing of blue waters. And we implemented our code using hybrid MPI OpenMP approach. And it turns out that 95% on computing time now is spent on crunching the matrix elements. And only 3% is spent on solving the eigenvalue problem, which is good actually, because computing matrix elements is embarrassingly parallel problem. You can scale it really, really well, which is not true for eigenvalue problem. So the challenge is how you actually distribute the basis states between processes in such a way that you end up with a load balance computations. And here you can see three pictures of the same Hamiltonian with a different distribution of basis states. And it shows that we indeed found a way how to come up with a load balanced construction of basis and distributing between processes. So each process does the same amount of work. And finally, because we are dealing with an embarrassingly parallel problem, it's not surprising that we are getting excellent or good scalability both in MPI and hybrid OpenMP MPI approach. So the first step we had to do actually was to prove to the nuclear community that our basis is indeed physically relevant to the problem. So what we did is that the first, we take Nmax space and we take all basis states we have and we solve it in our basis and then depict the structure of the wave function. And this is what you get. You realize that actually not all configurations are equal. So you see the red color that corresponds to the lowest lying, the lowest spin that you can construct in lithium-6. And you see the red color highly dominates. So you can see immediately, why do I have to include in my basis all spins? No, it's not. You don't have to, because it's not important for all energy nuclear physics. And as you can see, everything, these large bars are on the right side of the histogram that shows you, and below you see the quantum numbers of lambda mu that corresponds to it. So you see that lithium-6 likes to be deformed as a cigar, right? And the larger value of lambda, the larger deformations. And so we found that using ab initio or realistic nuclear interaction that come from QCD, which are highly complex, you suddenly, in our basis, you get a simple picture that low spin and large deformation absolutely dominate low energy nuclear structure. And this finding was published recently in PRL. But the question is then, so this is lithium-6, this is ground state. What about other states? Another way how to visualize our model space, our basis, is using this. So here on a horizontal axis, you see the lambda mu SU3 quantum numbers, and on vertical you see intrinsic spin. And each circle in the graph corresponds to a subspace of configurations that carry given quantum numbers. So naively, if all states have same importance, or if interaction couples them or mixes them strongly, this is the structure of the wave function that you should see, right? And when we do calculation for lithium-6 and other states in lithium-6, this is the picture that we get. On the left side, you see what would happen if you would have equal probability. And then you see the ground state, 3 plus excited state, 2 plus excited state, 1 plus excited state. And they actually look as if I did copy and paste. This is because the lithium-6 gets deformed and then starts to rotate. And each of that states differs by just the way it rotates, how fast it rotates, right? But the deformation is the same. So this means that our basis is going to be extremely good for describing rotating deformed bodies. And one model space is going to work for a whole state, all states of rotational band. And of course, another question is, well, and then when you go to heavier nuclei, do you lose this feature or not? So we did calculation for oxygen 16. Of course, you have 16 particles, so you have much more spins, much more deformations. And you see that if all was equal, you would get quite a busy graph on the left side. However, this is what we got from blue waters. Only a few components are important, and the rest can be thrown into garbage. And so our scheme actually allows you to truncate the complete model space and restrict it to only few spins and few deformations. And so we proceed to SD shell nuclei, right? This is a nuclei that has much more protons and neutrons, and which was up to now, you couldn't reach it with a standard no-core shell model approaches. So what I show you here that we take all deformation and all spins up to some level that we can handle, where we can handle complete model space. And then beyond that, we choose only configurations that are important for the low energy physics. So the complete space dimension would be 7 billions, our basis is 3 millions, and you can see the results for silicon-24, which is actually impossible to obtain in experiment, and only a few states are known. So we have pretty good agreement with theory. We also observe states that have not been measured yet, so that is prediction. And next state, next nuclei we targeted on blue waters was neon 20. Again, the complete space was 4 to 10 to 12. So there is even no way you can be able to do it in complete space using exascale computers. You will have to go beyond if you don't want to do it equal. But we don't want to wait for exascale computers. We want to do it on blue waters. So again, we use our symmetry-adapted truncation scheme to restrict basis only on the most important deformation and spins. And we decrease the basis by 5 orders of magnitude. And again, we got excitation spectrum, which is very close to experimentalist measure. And to show some nice picture, I also show the nucleon density in neon 20, which actually shows some effects of clusterization. So the blob in the middle, that's carbon-12 nuclei, and around this is a torus that's made of 2 alpha particles. And finally, you can see binding energy. And now that takes me to the summary. So using blue waters and symmetry-adapted no-core shell model, we were able to show how collective modes emerge from first principles. We also come up with a brand new way how to truncate basis based on and construct physically relevant model spaces. And this allows us, with help of blue waters, to perform first ab initio studies of open shell medium mass nuclei. And the last picture shows the reach of symmetry-adapted no-core shell model on blue waters compared to other standard methods. Thank you.